Okay, so in this video we're going to take a look at second order ordinary differential equations, or ODEs. And this video is just meant as a simple introduction, so we're just going to look at some terminology, the general form, and the theory behind how we're going to solve them. So let's start out by taking a look at the general form of a second order ODE. Okay, so here we have a typical second order ordinary differential equation, where we have some function a of t multiplied by the second derivative of our term x. We have some function b of t multiplied by our first derivative of our function x, plus some function c of t multiplied by x is equal to some function. So at first it's not entirely obvious as to how we can actually go about solving this equation. However, there are a few tricks we can use in our algebra toolbox to be able to solve this. But first, let's take a look at another important definition that we're going to be using throughout these videos, and that's the definition of a homogeneous second order ODE. So if our d of t in this example is equal to 0, we call this a homogeneous second order ordinary differential equation. However, if it is not equal to 0, then we refer to these as a non-homogeneous ordinary differential equation. And there's a big difference in how we go about solving these equations as well. However, if we have a non-homogeneous second order ordinary differential equation, then we can still find the solution of the homogeneous equation in order to express a solution of the non-homogeneous. And then we can use initial conditions to solve it even further. So in order for us to solve a homogeneous second order ordinary differential equation, we can use what's known as a lambda substitution. And all the lambda function is just taking the derivative. So the lambda function is defined as the derivative by dt in this example of our function, whatever we insert here. So then by this definition as well, we have a lambda squared function. So we just perform the lambda function, and then we perform the lambda function again, which will give us the derivative of whatever we put in here. So this will just be the second derivative of our initial value that we insert here. So if we apply our lambda substitution to our equation up here, and we just take the homogeneous solution, so we put d of t is equal to 0, we'll be left with, and just for convenience we'll drop the function notation here just so it looks a little bit neater, we'll be left with a lambda squared plus b lambda plus c is equal to, and as I mentioned earlier, we can make this equation homogeneous just so we can get an initial solution and then take what we get from the homogeneous solution in order to evaluate the final non-homogeneous solution. So equals to 0. And now hopefully it's obvious that you can use the quadratic formula or factorization, assuming that you know what a, b and c are, in order to solve for lambda. And by doing so, we'll find that there are 3 possible solutions. The first will be that lambda 1 is not equal to lambda 2, because a lot of the time we have 2 solutions for lambda, so these are just depicted as lambda 1 and lambda 2. The second is that lambda 1 could be equal to lambda 2, so you have a repeated root and we would just call this lambda. And the final possibility is that lambda could be equal to some real part, we'll call it mu, plus or minus some imaginary part multiplied by, we'll call it nu. This is the Greek letter mu and the Greek letter nu. So then, depending on what our values for lambda 1 and lambda 2 are, means we'll have a different general solution for this ordinary differential equation, and then we can just go about solving the general form. So for example, if we have two real roots to this problem, our general solution, x of t, which is just the x we're solving for here, will be equal to some constant, c1, multiplied by the exponential of lambda 1 t, plus another constant, multiplied by the exponential of lambda 2 t. Then if we have a repeated root, so we have a single lambda, our x of t will be equal to c1 times e to the lambda t plus another constant c2 multiplied by t e to the lambda t. And in our final example, our x of t, we can use Euler's relations to give us that this will be e to the real part multiplied by t, and that will be multiplied by some constant again, c1, times the cosine of the imaginary, nu t, plus another constant multiplied by the sine of nu t. So hopefully this video has proved to be a good introduction to second order ordinary differential equations, and hopefully it's given you a little bit of an insight into how we're going to go about solving second order ODEs as well. As always, if there are any questions or comments, please feel free to ask them in the box below. And in the next video we're going to look at solving simple homogeneous second order ODEs. We'll see you there.